Hello again. We are looking at statistical inference. This is the third video we're looking at. Last session we established that we've got an expected value of the sample proportion is in fact the same as the population proportion. And our standard deviation of our sample proportion is given by this rule. Now that's very important. We're going to be drawing on them. So let's try and apply them to this problem. So we've got n equals, capital N equals 1,500. Now that's the population. Now the population isn't needed in working at our mean or our standard deviation. So we have to be ready to pick up the fact that we only need small n, which is our sample size. Okay. And we've got our proportion, population parameter of 0.15. So let's find the mean and standard deviation for the distribution of a sample proportion, p hat. Alright, so first off, the mean, well, that's our expectation value of p hat. Now, what was that the same as? Well, it was in fact same as the population proportion. Okay, 0.15. So there's no calculation here there. You just need to recognize that the mean of the sample proportion is the same as the population proportion. That's the expected value. Alright, now what about the standard deviation? So our standard deviation is given by this rule. Alright, that is now the population parameter. So this is standard deviation for p hat and the mean for p hat. Okay, just so we can be clear on what we're finding. So the square root divide n. Now the whole n, remember the sample size n is also inside the square root in the denominator. So this little calculation is an important one to practice. So here we go, we've got 0.15 times 1 minus 0.15, all divided by sample size of 150. And we take the square root of that number. Okay? And that is usually needs to be done on a calculator like the CAS. So there it is, there's our calculation. And we get this value as exact amount and approximately 0.029. Okay, so to 3 decimal places, 0.029. Is that correct? So always make sure you double check. Yes, it is. 0.029 to 3 decimal places. Alright, fantastic. Alright, get the idea? So calculating the mean and the standard deviation. The mean is just a recognition. That's the same as P, our population proportion. Alright, now what's important about the mean and standard deviation of our sample proportion? Well, on the assumption for large samples, okay, if samples are large, then what we need to consider is the distribution of our p hat is approximately normal. Okay, so if you collect enough people in your sample for a survey, for instance, then we start to get the proportion of the observed outcome to be normally distributed. And that's the important thing. This will be the mean of the normal distribution and our standard deviation. It can be of the normal distribution of p hat can be found like that. Okay? So here's an example of a normally distributed sample proportion p hat. Okay? This sample size is about 50 for a population of about 1,000. And there's our population proportion. That's the expected amount. Well, that appears right in the mean. So there it is. About here is our mean amount. Alright, right in the center. And our standard deviation is approximately, there's that width. either side. And so all our ideas we know about the normal distribution we can apply now to our distribution of p hat. Okay, very good. Now, the question is, what is considered a large sample? How do we know if the sample we have is a large one? There's a number of different methods to determine whether a sample size is large enough for the population. The most easiest one to work out what's to get an appropriate sample size that's considered large enough is just the square root of the population. That's the most straightforward one. Okay, so in this case the square root of the capital N number, and that can give you an idea of how big your sample needs to be for it to satisfy the assumption that it's approximately normal in distribution. Okay, so for this example, our square root of n is the square root of 1000. Okay, so let's see if it satisfies. Bit off the cuff. Okay, so a sample of greater than about 32, that is considered to be large enough for the assumption of approximately normal distribution is satisfied. Okay, so as long as the sample is bigger than that number, then we're all good. Okay, fantastic. Tick, tick, it's 50, much better. All right. So now that we've got the idea that it's not approximately normal distributed, we're going to draw on that and see how we can use our mean and our standard deviation in different ways. So when we have a situation where we've got the population and the sample, very good, we can use information about our population proportion P. Okay, and from that we can calculate some important parameters, some important statistics on our sample, our mean and our standard deviation. But sometimes population might be unknown. We don't know how many people there are in the population, or it's too difficult to count and work out what is P, because it might be too big or not enough information. So sometimes P is unknown, and that's an important thing. Sometimes it might be unreliable. Sometimes claims might be made about a population, and we want to test those claims. Okay, so how do we go about doing that? Well, the best thing we've got is our sample. The sample is what we have to work with. Okay, so we sample our population. As long as the sample is big enough, remember square root, the population size is reasonable. So as long as we get a big enough sample, we can use the information we figure out about the sample to determine things about our population. So the sample statistic, they become the best estimates we have for the population parameters. And they just are estimations. So the distribution of P is approximately normal, as long as that's still satisfied, as long as the sample is large enough. Then now the mean of our sample distribution is in fact the same amount, the sample proportion. And our standard deviation becomes the sample proportion is used in the formula. These are just approximate values, these are estimates. So when we don't know the population parameters, we have to use the sample statistics. Alright, so this is going to bring us to now the idea of confidence intervals. So what is a confidence interval? Well, if you don't know what the population parameter is, or we're trying to test a claim made on the population parameter, so we want to be able to come up with an interval or a range of numbers that we could say, well, I'm pretty confident that the true population proportion, which I don't really know, is roughly in between these two values. Okay, so we can accurately do that. So we can use the sample proportion, p hat, to form an interval of values for which the true population parameter may reside. Okay, so we're going to draw on what we know about the sample to say things about the population. Now the width of the interval, the range of how big those range of values are, for p, is such that we speak with degrees of confidence that the true value is within that interval. So I might say, oh, well, I'm 90% confident, I'm 80% confident, 99% confident is probably the best. Now the interval is formed by using multiples of standard deviations from the mean. Okay, so we're going to do that by drawing on the assumption we've made. It's approximately normal distribution of p hat. Because it's a normal distribution, we're going to draw on the idea of the standard normal distribution, our z-score. So our z-score on p hat, which is our parameter, our value now, continuous random value, we have this subtract the mean, divide by standard deviation is our z-score. Okay, where the mean is in fact p. Very good. So this is what we're after. Just by swapping and rearranging that, solving it for p, we get this expression. So it says let's start, p values can be found by, let's start with p hat, and we can add and subtract values of z. Now z, we can say add and subtract values of z because they can both be positive and negative, especially when it's the standardized z-score, isn't it? Because the mean is 0 and the standard deviation is 1. Okay, multiplied by some standard deviation. So that produces intervals. So an approximate confidence interval for the population proportion, p, is given by this. So the interval is the smallest number to the largest number, p hat minus z times standard deviation on p hat is the smallest, and the maximum is the p hat plus the z times standard deviation on p hat, where this is going to be our standard deviation. It's our estimate, okay, because we don't know what the population proportion is, so we have to use our p hat, our sample proportion, as our estimate value, as our estimator. All right, so here we go. So let's think about amounts of confidence we're going to speak of. Now, any level of confidence can be chosen. A level of confidence is expressed as a percentage. So the usual confidence limits are 95% confident or 98% confident, or the best one, which many pharmaceutical companies demand, is 99% confidence in their statistics that they're trying to report. So the higher the level of confidence, what will happen, it's going to make the width between the interval on p bigger and bigger. It's going to have a greater range of numbers in between your confidence interval. So you can think about that in terms of our distribution on p hat. The mean is p, so we can spread out the area around the mean is going to spread out and get longer and longer, and so we will have smaller amounts of area in the tail, and the width is going to be wider. Okay, so the confidence level is used to find the multiple of deviations from the estimated mean value p. So the multiples of deviations is in fact the z number. Okay, z is some multiple of our deviation, our standard deviation. So we have to work out how big of these multiples we want. So let's look at an example. So for a 95% confidence interval, we're saying that the probability of our p hat being in between this range of values is 95%. Okay? That's what we mean by 95% confidence. Now, what we're needing to recognize is that this value down here, that's our lower bound, our p hat minus z times sigma. So the probability that of all our p hats less than that value is the tail, the little area of the tail, okay? Which will be for 95%, we've got 2 tails. So how much is left over? If the blue area is 95%, how much is left over? Well, we got to subtract it away from 100%. So we've got 5% in the 2 tails. How much in one tail? We have to halve. So this becomes a standard procedure to find the position of our number. So the probability of one tail is 2.5%, 0.025. And same here, the probability that our p hats are greater than this amount is 2.5%. So once that's established, we say, well, we don't really know what p hat, what this number is, because z is unknown. Well, let's standardize that. Let's relate this probability now to our standard normal curve. So this really, we're going to think about it in terms of the standard normal curve. And we know things about the standard normal curve. We have a mean for our standard normal curve of 0. And we have a standard deviation of z of 1. That becomes very useful. What's here? Nothing. Okay, moving on. So this probability statement here, we're going to grab that one. On the fly. This is unscripted. The whole lot's unscripted. Here we go. So we've got our 2 probability statements. Ooh, okay. Ooh, the whole lot. Okay, fair enough. These 2. Now they are equivalent probabilities. What is the z number that is equivalent to this for a mean of 0, a standard deviation of 1? Well, we do inverse norm on the CAS. Okay, so for a probability of 0.025 for a mean of 0, standard deviation 1, we get this as our z number. So that being our z number, we can also say that, well, what about at the other end? This is a negative z number, this is this part. What about the other end, where we've got 0.975 at the other end? Well, here, again, if we take probability of 97.5%, we get a positive version. So we get both the plus and minus of the same z number. So that's hence why we get our confidence interval. We've got both a plus and minus version of it. Okay, so let's figure out how we're going to calculate a confidence interval. Alright, the first thing we're going to do is we have to identify what is the sample proportion p hat. Once that is done, then we determine the area of the tail, just like the idea we outlined previously. Doing so by looking at the confidence that we're wanting, the confidence level, like 95% or 98% confidence, and we go 1 minus that, and that gives you what the total area, what's left over. And this white area here and this white area here. And then we have to halve that. So we're interested in just what is the size of 1/2 of the area that's left over. Now that's going to give us one of these probability statements in terms of the standard normal curve z. And so we can use our inverse normal function on the CAS to get a z-score. Okay, so once achieved our z-score on the CAS, then we calculate a standard deviation. We're going to calculate it using the sample proportion as our best estimate, and we're going to use the formula for the standard deviation of the sample proportion. Then we multiply them two together, the z-score times the standard deviation, and that gives this part of the interval. That is what we call the margin of error. And we put it together with the confidence interval. So
we add it onto p hat and subtract it from p hat. And there we have it. Okay, so let's examine this problem. It says, of 53 people at the swimming training today, 82% said that their favorite stroke is freestyle. So let's estimate the proportion of the population whose favorite stroke is freestyle. And let's find a 95% confidence interval for the estimate. Alright, so first thing we're going to recognize is that we have a sample that's present of 53 people. Okay, so that's the sample size. And the sample is surveyed, and we've got a proportion, 82% of them have said yes, that their favorite stroke is freestyle. Okay, so the sample size, the sample proportion in this case is the 0.82. From that, we need to find a 95% confidence interval. So let's state the confidence interval. And so the area of the tail is 1 minus 0.95, which is 5%, divided to 2.5%. That's the area of one tail. So we use the inverse norm function for that on that area, 0.025 for for a mean of 0 and a standard deviation of 1, and we get our z number. There's our z-score number. That is the multiple of standard deviations on either side of our sample proportion that we need for our confidence interval. Okay, so next step, let's multiply those two amounts together. So the z times the standard deviation, and now this is where we use our formula to calculate it. So 1.95996 times the square root of 0.82 times 1 minus square root. The 1 minus 0.82, divide the sample size 53. And we get this result. Alright, let's put it together in the confidence interval with our p hat 0.82. So we add that amount to 0.82, get this, and we subtract that amount from 0.82. Very good. So there's our two values. Now let's interpret our results. So essentially saying here that we can see that the lower bound is about 71.7%, and the maximum is 92.3%. And we can be 95% confident that the proportion of the population that favor freestyle is between those two proportions. Okay, and there we have it. We've constructed our 95% confidence interval. Well, I hope learning about statistics has been interesting, and we have finished that area of study. Well done.